So now let's conclude our discussion of section 4.2, which is a basic introduction to logarithms, their definition. We looked at the graphs a little bit, and now let's do a couple more topics. If you start thinking about calculators and evaluating logs, there's always two buttons on any scientific calculator, including our TI-84s, or TI-83 if you have an 83. There's a button, let me pull the one onto the screen here and look at the 84. They're right here on the 84. There's a log without a base written, just LOG log, and then there's this LN button. Their inverses are actually above them on this calculator. You see 10 to the x and e to the x. And so there's these two logarithms that are used so often that they put them on most all scientific calculators. So there's the common log, which is what they call it, which is base 10. We have a base 10 number system, so we use powers of 10 a lot. So you have the logarithm base 10. So in this class, if you see log of x written without a base, you assume it's 10. Then there's also the natural log. E is used so much in mathematics. It turns out in advanced mathematics and applications just all over the place we use E so much that they put the inverse of it on the calculators, which is called the natural log, because we called E the natural base. The natural logarithm is base E. And they write that as Ln for the natural log. The logarithms were invented by a French mathematician, and they reverse adjectives and nouns. So instead of NL, we have LN. Okay? Again, you have those two buttons on the calculator. I'm going to go ahead and show you, if you have the newest operating system on your calculator, and if you have a TI-84 and you don't, you can actually upgrade that. I can do that with my calculator. But if you do, if you hit the alpha button and the buttons under the window, you get different options. Like if you want to do a fraction, you can do alpha and that button. But if you do alpha and the window button, the second one, you get some different function setups. And if you go down to number 5, this is also buried in the math menu, but this is a shortcut. If you hit alpha and the window button, you get the template to do logs of other bases. So if you wanted to do like log base 3 of 9, you could do that. Okay. There's actually a thing we'll look at in 4.3 called the change of base formula, where you can evaluate any logarithm with natural log or common log, which is why most calculators only have those. But you know, we got our fancier calculators now. If you have the newest version, you can do other logs. But you have, if you're doing base E, base 10, quick and easy, you have buttons directly for that. Okay. So let's finish this up by talking about domain. The domain of logarithmic functions. So logarithms are the inverses of exponentials, and exponentials are always positive, strictly greater than 0. They'll never be 0, they'll never be negative. So when you look at their inverses, logarithms, you can't put 0 or negative numbers into them. You can only put in positive numbers. So if you want to find the domain of a logarithm, you have to figure out where is the inside positive. Okay. So for natural log of negative x, that would be a real number if the inside were positive, if negative x was greater than 0. And you can either add x to both sides or multiply and divide by a negative and flip the sign, and you wind up with x less than 0. So the domain of natural log of x is positive numbers. The domain of negative natural log of x is negative numbers. I've got the calculator handy. I'll go ahead and graph that. Again, if you look at natural log of x, you get the nice logarithmic function here. And if you do negative x, you get the reflection. We can think about, we know this, it's the reflection across the y-axis. It's defined for negative numbers. The domain is negative infinity to 0. It's always nice to be able to go back and forth between the symbolic algebra and graphs. They're two different ways of seeing the same thing. Okay. Part B, a little more complicated now. We have a 2x minus 7 inside, and it doesn't matter what the base is. In terms of domain, you just have to make sure the input's positive. But for part B, the input is 2x minus 7, so you could set up the inequality. 2x minus 7 is greater than 0. Isolate x, add 7 to both sides, divide by 2. Since it's a positive number, the inequality stays in the same direction. You get x is greater than 7 halves or 3 1/2. So the domain is 7 halves to infinity. And of course you always have parentheses on infinity because there is no endpoint, but it's important you have a parentheses on the other endpoint for logarithms, because when you plug those numbers in, you get 0 on the inside, and there's an asymptote at 0. Logarithms are undefined at 0, so it's strictly greater than 7 halves on part B. or strictly less than 0 in part A. Part C is a little more complicated because of the square inside. Same overall idea, you need to have the inside x squared minus 4 greater than 0 or x squared greater than 4. You can't just take the square root across an inequality. You have to think about that in some different way. Typical way we teach that is to look at the graph. This one, it's a pretty simple graph, x squared moved down 4, but I'll graph it on the calculator so we can see it here. So we're trying to figure out where's x squared minus 4 negative. If you take a quick look at the graph, it's 0 at plus or minus 2. So for a quadratic inequality, you can figure out where it's 0 and then look at this picture. It's positive on the ends, negative in the middle. So x squared minus 4 is positive from negative infinity to negative 2 and from 2 to infinity. So that winds up being the domain of the logarithm. Let's finish by looking at the graph of the original function then. So it was log, common log, base 10 of x squared minus 4. So an interesting graph here with the quadratic inside. And calculators always do a bad job with vertical asymptotes because they just plot points and these things shoot off to negative infinity so fast. There's actually a vertical asymptote at negative 2 and 2 that my calculator can't draw. And then the graphs, they go down to negative infinity on each side. So we see it's undefined between negative 2 and 2, and the domain are the other parts from negative infinity to negative 2 and 2 to infinity.